Algebraic Machine Learning, AML, is a set of mathematical concepts and computational techniques that allow computers to learn not only from data but also from formulas. With AML, it is possible to learn from just a problem description, like for example, learning to solve or create Sudokus without using data. AML is also capable of learning from data, just like neural networks, but it can combine data with prior knowledge given in the form of a set of formulas, so we can provide information we know about the problem. AML aims to extend the range of applicability of machine learning and to offer the user more interpretable models with more guarantees on correctness. In this video, we introduce the basic concepts that lie at the foundation of AML, including the notions of an algebra, subdirect decomposition, and semantic embedding. We will see that AML is a purely algebraic method that relies on principles very different to those underlying statistical methods. AML does not use error minimization or search methods you may be familiar with. In fact, AML does not try to reduce error. This simply happens as a result of decomposing the problem into its fundamental building blocks. We will give a few examples, and by the end of the video, our hope is that the viewer has a clear idea of how algebraic structures can be used to model data and find solutions to problems. Let's begin by defining an algebraic structure. An algebraic structure, or simply a structure or model, is a set of elements and a collection of operations defined over the set. Here we have defined an example of an algebraic structure with 4 elements and 2 functions, given by tables containing their input and output values. Mathematicians often fix some of the properties of their functions, called axioms, and leave everything else unfixed. For example, suppose we are interested in any model that has just one binary function f, that is commutative. We do not provide a specific set of elements or a particular table of a function. In this case, any set of elements and any table for f that satisfies the commutative property is an example, a model, of our requirement of having one commutative function. Models are different examples of mathematical structures that share a set of properties, an algebra. A group is an algebra with a couple operations, the product and inverse, and an identity element, all satisfying the axioms of associativity, identity, and inverses. Let's take a closer look at a specific algebraic structure, a semilattice. A semilattice has a single binary operation called the idempotent sum. This operation is commutative, associative, and idempotent. This means that when the operation is applied to any element x with itself, the result is that same element x. Let's check out a couple examples of semilattices. Consider the set M containing elements a and b, with the operation that sends a to a, and every other input to the element b. To see if this forms a semilattice, all we need to do is check that the definition is satisfied, namely that the operation is binary, idempotent, commutative, and associative. We can conclude that indeed, it is a semilattice. Semilattices can have any positive number of elements. To illustrate this point, another small example with 3 elements is given. This time, our set M contains elements A, B, and C, and the binary operation has the following function table. To see if it is a semilattice, all we need to do is check the definition. Since the requirements in the definition are satisfied, we have another semilattice. One way to create a new model is taking the product of 2 models. If we represent each component of a product as so, each element is a tuple that can be represented in a grid. We can also take the product of more than 2 potentially distinct models. In the case of 3, we get an orthohedron. Now the elements of the product are ordered triples. One may wonder if all models can be represented as a product of other models. While this would be useful, it isn't true in general. That doesn't mean we are all out of luck. We can instead use the subdirect product, which is a subset of a direct product with some additional properties. From this perspective, by taking a subset of the product, it means that only certain tuples of elements are permitted, and the rest are not. Not all subsets are subdirect products. They must also have algebraic structure. Moreover, we must be able to obtain every element of each component, in this case n and m, by projecting onto the component. This works with any number of components. The nice thing is, given any model, there always exists a subdirect decomposition. Let's consider a simple example with no operations. A standard piano has 88 keys. There are 7 full octaves and 2 incomplete ones. Since each key has a corresponding note and octave, we can decompose the keyboard as so. On the x-axis, we have each note of an octave, and on the y-axis, we have each octave. Notice how, even though certain combinations of octave and note are not available, the projection property is satisfied, so this is a subdirect decomposition. In the piano example, we have a model of an algebra with no operations. The model only has a set of elements, the piano keys, and no operations defined. Operations make things more complex, as our subdirect product should be compatible with the operations, but it also makes things more interesting. Another example is the Rubik's Cube. We all know the Rubik's Cube. You can rotate a side of the cube to change the position and orientation of a piece, but this movement also affects the position and orientation of other pieces. And that's the conundrum. But the subdirect decomposition can help us. The configurations of the Rubik's Cube form a model of an algebra, actually a group that we showed before. The elements of our model are the different configurations of the cube, and the operations are the rotations of the faces. Rotating a face of the cube transforms one configuration of the cube into another. There are more than 43 quintillion configurations of the cube. The Rubik's Cube has 8 corner pieces, each with 3 orientations, and 12 edge pieces, each with 2 orientations. A total of 20 pieces. Each of the 8 corner pieces can be at 8 possible corner locations, and each of the 12 edge pieces can be at any of the 12 edge locations. The possible configurations of the cube cannot be represented as a product of the corner and edge positions and orientations of the 20 pieces, simply because there are configurations that don't make sense. For example, we cannot have 2 corner pieces in the upper left corner location at the same time. Even more, if we put the corner piece in a different location, which gives 8 factorial configurations, each corner piece cannot have any of its 3 orientations. If we fix the orientation of 7 of the 8 corner pieces, the 8th piece can only have 1 orientation. Granted, we could disassemble the cube and put the last piece wherever we want to. However, we can never reach this configuration by rotating the sides of the cube. The same is true for the edges. If we set the orientation of 11 of them, the orientation of the last one is fixed. And there's more. Any rotation we do to alter the configuration of the corners affects the edges and vice versa. So we cannot use direct products here, but we can instead use a subdirect product. The subdirect product allows us to understand which configurations are possible and which ones are not. With some effort, the Rubik's Cube can be decomposed as a subdirect product of the corners and the edges, encapsulating how moving the corners and edges affect each other. Let's imagine for a moment that the composition of the cube into edge and corner pieces was unknown, and we only had access to how the different configurations transform into each other. In this scenario, we could represent each configuration with a number. By looking at how the group operations change the configurations and calculating the subdirect product, we can discover that the cube has corners and edges which are entangled the way they are. We will discover not only the pieces and their orientations, but how the motion simultaneously affects them. This subdirect decomposition explains why the heuristics to solve the cube work, and it is everything we need to know to design a strategy to solve the cube. We have seen how a real-world object, like the Rubik's Cube, can be described with a model, allowing us to compute a subdirect decomposition, discovering the edge and corner pieces, and understanding how these features relate to each other. Algebraic machine learning focuses on finding the independent or quasi-independent aspects of a problem and determining how these aspects relate to each other, decomposing the problem into its building blocks. To do this, first we have to represent the goal of the problem and the data we want to understand as a set of properties of an algebra. AML, then, calculates models that satisfy the properties and are expressed as a subdirect decomposition, which gives us the building blocks we are looking for. Although any algebra could be used, A convenient algebra is a semilattice that, despite its simplicity with a single binary commutative associative operation, gives us sufficient flexibility to tackle many problems. In order to represent the data or objects as axioms, we make use of a technique known as a semantic embedding. A semantic embedding is an encoding of the object or the data in a way that is compatible with the structure of the target algebra. This can be quite challenging, but a semantic embedding for one problem can be reused for a family of related problems. For example, images can be represented as concatenations of pixels. This semantic embedding can be used to solve pattern recognition problems in images and other data aggregations, including tabular data involving real numbers. For another example, let's say we want to recognize vertical bars in an n by n image in the presence of noise. As before, we can decompose images into sums of light and dark pixels. Given a set of positive examples in which the light pixels form at least one vertical bar, and a set of negative examples in which no vertical bar is formed, we then encode the positive examples in the algebra, obtaining a model equal to a subdirect product of components, each simultaneously mapping to the n vertical bars. We can also represent other complex objects such as a Sudoku puzzle. There is a semantic embedding that encodes the numbers, the cells, and the rules of the game in a semilattice. Once the subdirect decomposition is obtained, we can not only solve Sudokus, but generate new ones. The technique works for problems known to be extremely hard, even NP-complete problems, such as the Hamiltonian cycle problem, which consists of finding a closed path through a graph that visits every vertex exactly once. Given a graph, we can use constants to represent vertices, edges, and potential paths. In the semantic embedding, we combine these constants and impose constraints to encode the properties of a Hamiltonian cycle. For example, the fact that the path must visit each vertex exactly once. This technique can be used to find Hamiltonian cycles in the hardest of examples. In conclusion, we have seen some mathematical concepts that lie at the foundation of algebraic machine learning, in particular, algebraic structures such as semilattices, products and subdirect decompositions of models, and semantic embeddings. We have outlined how these concepts can be used to obtain the essential features of data, which can be applied to solve a wide range of problems.